Hi, now in this video we're going to be going through equals mc squared. We're going to do a worked example just to show you how to do the bits by hand. So we've got basically an equation for radium to go into radon via alpha decay. So alpha decay produces helium, and so what we need to do there is we need to work out the mass of our reactants and the mass of our products and find the mass defect. Right, so I might even do this bit and just show you another way of writing it. That might actually be quite useful. So let's do this in blue. So our mass defect M is equal to our reactants take away our products. Alright, so that's what we've got there. So if looking at our mass of reactant, that's obviously going to be radon, which is equal to 3.75. It's not 3.75. It's a funny way of writing this, but this is how it's being presented. 31927 by 10 to the minus 27. All right. Take the mass of our products. Now, our mass of our products is going to be 368.66419 by 10 to the minus 27 plus 6.64648 by 10 to the minus 27. Alright, so we can do that on a calculator to work out what our mass defect. So that's the key product, is to do that. So let's do that calculation. So it's going to be 375.31927, and then we're using our E, which is the little comma there, and that's minus 27. Take away, now we're going to put this in a bracket, okay, or you could work out the mass of the products separately and do the taking away. 8.66419 EE minus 27, and we're going to add, now just double check what that mass was. That mass was in our other thing, it was 6 point. Okay, so that's why the difference there, how they're doing that, just to make it easy for you so you don't make a mistake. So then that's 6.64648. That's right, and then that's e to the minus 27. And then close our bracket and enter. So the mass defect, that's the important bit, which is 8.6 by 10 to the minus 30. So that there is equal to 8.6 by 10 to the minus 30 kilograms is that mass defect. Working out our next bit, we need to work out our energy. So our energy is equal to delta M, which is our mass defect, times C squared. So that's going to be 8 by 10 to the minus 30 times by 3 by 10 to the 8, and that's squared. So now what I do is I go to my calculator. If I just go times, it's got the answer from the previous thing, times that by 3 to the 8, and then I square that, and that will give me my energy, which is 7.74 by 10 to the minus 13 joules. So come back to my document. So that's equal to 7.74 by 10 to the minus 13 joules. Now we need to convert this into electron volts. Okay, so the key thing when we're converting it to electron volts is we know the charge of an electron is 1.6 by 10 to the minus 19 coulombs. So therefore, to work out what my electron volt thing is over here, and we'll just change the color there, is that my energy is equal to 7.74 by 10 to the minus 13. Divide that by 1.6 by 10 to the minus 19. And that will give me my answer in electron volts. So let's do that on our calculator. So divide that by 1.6 EE to the minus 19. And that's going to give me 480 or 4,837,500. Okay, so that's what my answer will be in terms of looking at the number of electron volts. All right, and then to convert that to electron volts is what I need to do is divide that by a million. So divide that by 1 and then to the power 6. So that's going to give me 4.84, round it off to 2 decimal places, 4.84 mega electron volts. So this, we're going to write that down over here. Okay, so when we get that, we get let's do 4.8375 by 10 to the 6 electron volts, write it scientifically, which is equal to 4.84 mega electron volts. So for every nuclear reaction, their decay there, we're going to release 4.84 mega electron volts worth of energy. So that's the process of going through doing an equals mc squared question. So it's the reactants, take away the products, and hopefully we get a positive answer there, which will mean we get energy out. That's actually quite a useful process, right, to do that. All right, if you need any extra help, make sure you catch up with me in class.